Everything you learned about the speed of light is a lie. Scientists discovered a loophole so massive, so game-changing, that it makes interstellar travel not just possible, but inevitable. What they found is so disturbing, so fundamentally wrong, that some physicists wish they'd never looked. But now we can't unsee it. And here is a quick question. What's the first question you'd ask an alien civilization if we made contact with them tomorrow? Let us know in the comments. I will pin the most creative answer. Now let's begin. In late 2025, physicists published something extraordinary in the journal Classical and Quantum Gravity. For the first time ever, researchers presented a warp drive model that doesn't require the impossible. For 3 decades, scientists have known that warp drives could theoretically exist, but there was always one insurmountable problem. They needed something called exotic matter, specifically negative energy, something that violates the fundamental laws of physics as we understand them. This new research changes everything. To understand why this matters, we need to go back to 1994. That's when a brilliant Mexican physicist named Miguel Alcubierre published a paper that shook the foundations of theoretical physics. Alcubierre showed that within Einstein's general relativity, there's nothing that absolutely forbids faster-than-light travel. But here's the catch. You're not actually moving faster than light. Instead, you're bending the fabric of space-time itself. Think of space-time as a rubber sheet. Normally, when you want to travel somewhere, you move across that sheet. But what if, instead of moving across it, you could compress the sheet in front of you and expand it behind you? You'd essentially be surfing on a wave of space-time itself. That's the Alcubierre warp drive. The ship sits inside a bubble of normal space-time while the universe moves around it. From the perspective of someone inside the bubble, you're not even moving. But from the perspective of someone watching from outside, you're racing across the cosmos at speeds that would make light itself seem slow. Here's where it gets fascinating. Einstein's theory of relativity tells us that nothing can move through space faster than light. That's an absolute speed limit. But Einstein never said anything about space itself moving faster than light. Space can expand or contract at any speed it wants. In fact, we see this happening right now in our universe. Distant galaxies are moving away from us faster than light because the space between us is expanding. The Alcubierre drive exploits this loophole in the laws of physics. But there was always a problem, and it was a big one. When physicists calculated how much energy you'd need to create an Alcubierre warp bubble, the numbers were absurd. You'd need more energy than exists in several galaxies. And worse, you'd need negative energy, a form of matter that repels gravity instead of attracting it. In our everyday experience, all matter and energy have positive mass and positive energy. They pull things together through gravity. Negative energy would push things apart. It would be the opposite of everything we see in nature. Now, negative energy isn't completely impossible. There's a phenomenon called the Casimir effect, where 2 metal plates placed incredibly close together in a vacuum will experience a tiny attractive force. This happens because the quantum vacuum between the plates has slightly less energy than the vacuum outside them. In a sense, the space between those plates has negative energy relative to the surrounding space, but we're talking about minuscule amounts of energy, far too small to power anything like a warp drive. For years, this seemed like an insurmountable barrier. Warp drives were mathematically possible, but physically impossible. They existed on paper, but could never exist in reality. Scientists filed them away in the same category as perpetual motion machines and time travel to the past, beautiful ideas that nature simply doesn't allow. Then in December 2025, everything changed. A team of physicists led by Harold "Sonny" White, who previously worked on warp drive concepts at NASA's Johnson Space Center, published a revolutionary new design. Instead of a smooth ring of warped space-time surrounding the ship, they proposed something called a segmented warp drive with discrete cylindrical structures they called warp nacelles. If you're a Star Trek fan, yes, they actually used that term, but this isn't science fiction anymore. If you are enjoying this deep dive into the cosmos and want to see more content like this, please take a second to give this video a like and hit that subscribe button. It really helps this channel grow and allows me to bring you more fascinating science content. What makes this design special is that it dramatically reduces the amount of exotic negative energy required. The original Alcubierre drive needed negative energy equivalent to the mass of Jupiter. White's refined design from years ago reduced that to something closer to the mass of the Voyager spacecraft, about 700 kilograms. This new segmented design takes it even further. The energy requirements drop by a factor of 38 compared to the original Alcubierre metric. But here's the real breakthrough that happened in late 2025. A separate team of researchers published a paper in General Relativity and Gravitation showing the first warp drive model that uses predominantly positive energy. Let me repeat that because it's so important. Predominantly positive energy, not negative energy, not exotic matter that might not exist. Regular, normal, positive energy that we know exists in our universe. This new model is what physicists call an irrotational warp drive. It's based on a mathematical approach that eliminates vorticity in the space-time flow. Without getting too deep into the mathematics, vorticity is basically swirling or rotational motion in the space-time fabric. The researchers discovered that by designing a warp field with zero vorticity, they could create a warp bubble, that's what they call Hawking-Ellis Type 1, throughout all of space. This is a technical way of saying the energy conditions make physical sense everywhere, not just in certain regions. The numbers are stunning. Compared to the traditional Alcubierre design, this irrotational warp drive reduces the peak negative energy deficit by a factor of 38. Compared to another warp drive design called the Notario metric, it reduces negative energy by a factor of over 2,600. The peak violation of what physicists call the null energy condition, one of the fundamental requirements for normal matter, is 60 times smaller than in previous designs. What does this actually mean in practical terms? It means we've gone from needing impossible amounts of impossible matter to needing challenging but potentially achievable amounts of mostly normal matter. We've moved warp drives from the realm of pure fantasy into the realm of extremely difficult engineering. But let's be honest with each other. Even with these improvements, we're still talking about energy requirements that are far beyond anything humanity can currently produce. The total energy output of our entire civilization is still dwarfed by what would be needed to create even this improved warp bubble. We're not building starships next year or even next century, but for the first time in history, we can say that warp drives are not fundamentally impossible, they're just really, really hard. Now, to understand why this breakthrough matters, we need to understand what a warp drive would actually do. Imagine you're standing on a beach, and there's a ball floating on the water 10 meters away from you. You could swim out to the ball, fighting against the waves and currents. That's like conventional space travel. Or you could somehow create a current that brings the ball to you without the ball actually moving through the water. That's closer to how a warp drive works. In the warp drive scenario, your spaceship sits in a small bubble of flat, normal space-time. The bubble itself is about 10 times wider than your ship. Everything inside this bubble experiences normal physics. Time flows normally. You feel no acceleration. You could be sipping coffee and wouldn't spill a drop. But outside the bubble, space-time is being dramatically warped. In front of the ship, space contracts. Distances shrink. Behind the ship, space expands. Distances grow. The net effect is that your bubble of flat space-time moves through the universe, carrying you along with it. From your perspective, inside the bubble, you're completely stationary. You're not moving at all. But from the perspective of someone watching from Earth or from your destination, you're covering vast distances in impossibly short times. You could travel to Alpha Centauri, 4.3 light-years away, in a matter of weeks or even days, depending on how fast you can make your warp bubble move. Now here's something mind-bending. Because you're not actually moving through space, you're not experiencing time dilation. In Einstein's special relativity, if you travel close to the speed of light, time slows down for you relative to people who are stationary. Travel at 99% of light speed for what feels like 1 year to you, and when you return home, decades might have passed on Earth. This is called the twin paradox. But with a warp drive, there's no time dilation. You could travel to a distant star and back, and when you return, the same amount of time will have passed for you as for everyone back home. This is actually crucial for interstellar travel. Without warp drive, even if we could build ships that travel at 99% of light speed, the time dilation effects would make it incredibly difficult to maintain any kind of civilization spanning multiple star systems. Travelers would age slowly while everyone they knew back home grew old and died. With a warp drive, this problem disappears entirely. But let's talk about the challenges that remain because they're substantial. First, even with predominantly positive energy, these new warp drive models still require some negative energy. Not as much as before, but still some. Where does that come from? The Casimir effect I mentioned earlier produces tiny amounts of negative energy, but scaling that up to useful levels is a massive engineering challenge. We're talking about creating enormous arrays of precisely manufactured plates separated by distances smaller than the wavelength of light, all maintained in perfect vacuum conditions. It's technologically daunting. If you're fascinated by particles that might already be breaking the cosmic speed limit, you should definitely check out my video on tachyons and how they challenge our understanding of causality and the structure of space-time itself. It dives deep into the physics of hypothetical, faster-than-light particles and connects beautifully to what we're discussing here about warp drives. I'll put the link in the description and on the card above. I am sure you'll enjoy it. There's the problem of navigation and control. How do you steer a warp bubble? How do you start it and stop it? The mathematics of the warp drive show that once you're inside a warp bubble, moving at superluminal speeds, you cannot send signals to the front edge of the bubble because those signals would have to travel faster than light relative to you. You'd be cut off from the front of your own warp field. Some physicists have proposed that you'd need to pre-program your journey before you start, setting up a kind of space-time GPS that guides the bubble to its destination. But the details of how this would work remain unclear. Third, there's what's called the horizon problem. When your warp bubble moves faster than light, an event horizon forms around it, similar to the event horizon around a black hole. This was discovered by physicist William Hiscock. Anything that crosses this horizon gets trapped and can't escape. Even worse, as your warp bubble travels through space, it would sweep up particles, radiation, and even the quantum fluctuations of empty space itself. All of this would accumulate at the front edge of your warp bubble. Here's where it gets dangerous. When you finally slow down and turn off your warp drive, all of that accumulated energy would be released in a catastrophic blast of radiation aimed directly ahead of your ship. Some calculations suggest this burst of energy could be powerful enough to sterilize entire planets. Imagine arriving at a pristine alien world only to inadvertently destroy it with the radiation blast from your own arrival. This is sometimes called the warp drive death ray problem, and it's a serious concern that physicists are still trying to solve. Fourth, there are fundamental questions about causality and time travel. Some solutions to Einstein's equations that allow faster-than-light travel also allow closed time-like curves, which are basically paths through space-time that loop back on themselves. In other words, time travel to the past. Most physicists believe nature has some mechanism to prevent time travel paradoxes, perhaps what Stephen Hawking called the chronology protection conjecture. But we don't know for sure how or if this works. It's possible that any attempt to create a warp drive would trigger some unknown physical process that prevents the warp bubble from forming. Despite all these challenges, the fact remains that we now have theoretical models of warp drives that don't obviously violate the known laws of physics. This is genuinely new. Just 5 years ago, most physicists would have told you that warp drives require exotic matter that almost certainly doesn't exist in useful quantities. Today, we have peer-reviewed papers in prestigious journals showing warp drive geometries that use predominantly normal matter. Let's talk about the actual physics behind how space-time bending works, because this is where the beauty and strangeness of general relativity really shines through. Einstein's theory tells us that mass and energy curve space-time, and that curvature is what we experience as gravity. The sun doesn't pull on Earth with some invisible force. Instead, the sun's mass curves the space-time around it, and Earth follows the straightest possible path through that curved space-time. We call that path a geodesic. Now, the Alcubierre metric, which is the mathematical description of the warp drive, creates a very specific kind of space-time curvature. It's not like the curvature around a star or a planet. Instead, it creates what we call a shift vector. This is a mathematical object that describes how space is being pushed and pulled in different directions. In front of the ship, the shift vector compresses space. Behind the ship, it expands space. The ship itself sits in a region where the shift vector is 0, meaning space-time is completely flat and normal. The elegance of this design is that the ship never accelerates. Acceleration is what you feel when you're pushed into your seat as a car speeds up, or when you're thrown forward as it brakes. With a warp drive, there's no acceleration at all. The ship is always at rest relative to the local space-time around it. This means no inertial forces, no g-forces, no stress on the ship's structure. You could build your warp ship out of tissue paper and it wouldn't matter. The ship itself experiences nothing unusual. But here's something crucial that many people misunderstand. The warp drive doesn't create a tunnel through space or a shortcut. It's not like a wormhole that connects two distant points through a higher dimension. The ship actually travels the full distance between its starting point and destination. It's just that the space in front of it is being compressed, so the distance becomes shorter, and the space behind it is expanding, making the distance you've already traveled longer. The total journey distance, measured in the ship's reference frame, is exactly what you'd expect from a conventional journey. What makes this faster than light is that from the perspective of a distant observer, someone watching from far away, the ship appears to cover vast distances in very little time. If you measured the ship's position every second, you'd see it moving many times faster than light. But locally, right at the ship's location, nothing is moving faster than light. The light speed limit is preserved. This is the loophole that makes the whole thing theoretically possible. Now let's address something important. Why can't we just use conventional propulsion to go faster and faster until we exceed light speed? Why do we need this complicated space-time warping? The answer comes from special relativity. As you accelerate closer and closer to the speed of light, something strange happens. Your mass increases. Or more precisely, your relativistic momentum increases. The faster you go, the harder it becomes to go even faster. At 99% of light speed, you're already experiencing significant mass increase. At 99.9%, it's even more dramatic. By the time you approach the speed of light, your mass approaches infinity. To accelerate an infinite mass requires infinite energy, which doesn't exist. This is why light speed is a barrier. It's not just a speed limit like the speed limit on a highway that you could break. if you tried hard enough. It's a fundamental feature of how space-time works. No amount of conventional thrust, no matter how powerful your engines, can push you through this barrier. But the warp drive sidesteps this entirely. You're not accelerating through space. Space itself is moving, and space doesn't have mass. Space can expand or contract at any speed without requiring infinite energy. During the first fraction of a second after the Big Bang, space expanded far faster than light. Even today, the most distant galaxies are receding from us faster than light because of cosmic expansion. Space is not bound by the light speed limit. Only objects moving through space are bound by it. This brings us to one of the most beautiful aspects of warp drive physics. The mathematics that describes the Alcubierre warp drive is the same mathematics that describes the expanding universe. In fact, some researchers have pointed out that we're already living in a kind of warp drive universe. The space between galaxies is expanding, carrying them apart faster than light, while the galaxies themselves remain at rest relative to their local space-time. The warp drive just applies this principle on a much smaller scale and makes it controllable. Let's talk about energy density for a moment, because this is where the recent breakthroughs become so significant. In the original Alcubierre design, the negative energy density required was enormous. We're talking about energy densities billions of times greater than anything we can produce in a laboratory. Even the most powerful particle accelerators, machines that slam protons together at nearly light speed, produce energy densities that are infinitesimal compared to what the original warp drive needed. The new irrotational warp drive design, the one published in December 2025, changes this calculation dramatically. By eliminating vorticity in the space-time flow, the researchers created a geometry where most of the energy is positive and only a small fraction is negative. The negative energy is still there, concentrated in specific regions around the warp bubble, but the total amount is vastly reduced. Here's a way to visualize this. Imagine you're trying to create a hill on a flat field. One way to do it is to dig a giant hole and pile all that dirt into a mountain. That's the old Alcubierre drive. Huge amounts of negative energy creating huge amounts of positive curvature. The new approach is more like using the natural contours of the land, adding small amounts of dirt in strategic places and removing small amounts in others. You end up with the same hill, but with far less excavation required. The researchers quantified this improvement using something called the weak energy condition and the null energy condition. These are principles in general relativity that describe what kinds of energy densities are physically reasonable. Normal matter satisfies these conditions. Exotic matter violates them. The new warp drive design minimizes the violations. In some regions of space around the warp bubble, the energy conditions are actually satisfied completely. Only in small specific locations are they violated, and even there, the violations are much smaller than in previous designs. Does this mean we could build one with current technology? Absolutely not. Even with these improvements, the energy requirements are still astronomical. We're talking about energies equivalent to the total power output of a large star, concentrated in a region smaller than a house. No technology we have or can envision in the near future could achieve this. But we've moved from needing the energy of an entire galaxy to needing the energy of a star. That's progress. There's also the question of stability. Would a warp bubble, once created, hold together? Or would it collapse or, worse, explode? Some early research suggested that warp bubbles might be inherently unstable, that small perturbations would grow and tear the bubble apart. The quantum vacuum fluctuations of empty space, the constant bubbling of virtual particles popping in and out of existence, might be enough to destabilize the bubble. More recent work has been more optimistic. The irrotational design appears to be more stable than the original Alcubierre metric. The absence of vorticity means there are no internal shear forces trying to twist the bubble apart. But stability analysis is complicated and ongoing. We're dealing with extreme curvatures of space-time in the presence of quantum effects, and we don't have a complete theory of quantum gravity to guide us. This is one area where theoretical work is desperately needed. There's another aspect of warp drive physics that deserves our attention, something that connects to the deepest questions in cosmology. The universe itself is expanding, and that expansion is accelerating. We attribute this acceleration to something called dark energy, a mysterious form of energy that permeates all of space and pushes the universe apart. Dark energy makes up about 68% of the total energy content of the universe, yet we have no idea what it actually is. Here's where it gets interesting. The mathematical description of dark energy in cosmology looks remarkably similar to the mathematics of the expanded space behind a warp bubble. Both involve regions of space-time with unusual energy properties. Some physicists have wondered whether we could somehow harness dark energy to power a warp drive. If we could manipulate dark energy the way we manipulate electromagnetic fields, we might be able to create warp bubbles without needing exotic matter at all. This is highly speculative, but it illustrates how warp drive research connects to fundamental questions in physics. We don't understand dark energy. We don't understand the quantum structure of space-time at the smallest scales. We don't have a working theory of quantum gravity. Warp drives sit at the intersection of all these unknowns. By studying warp drives, even just theoretically, we're forced to confront these deep questions. Let's talk about what a warp-capable civilization might look like. If we assume that the engineering challenges can eventually be solved, what would change about human civilization? The first and most obvious change is that the galaxy would become accessible. Right now, even with optimistic projections about future propulsion technology, interstellar travel seems impossibly slow. A journey to the nearest stars would take centuries with conventional rockets. With warp drive, that same journey could take days or weeks. This would transform humanity from a single planet species confined to one tiny corner of one galaxy into a truly spacefaring civilization. We could establish colonies on distant worlds without condemning the colonists to a one-way journey lasting multiple generations. We could explore thousands of star systems, searching for life, for resources, for knowledge. The galaxy would become our neighborhood instead of an unreachable cosmic wilderness. But there would be challenges beyond the merely technical. How would governments and laws work across light years of distance? Even with warp drive, instantaneous communication wouldn't be possible. Radio waves still travel at light speed. If you're on a colony orbiting a star 10 light-years from Earth, any message to Earth would take 10 years to arrive, and the reply would take another 10 years to reach you. Warp drive gives you fast transportation, but it doesn't give you fast communication unless you physically carry messages back and forth. This creates a strange situation where information travels faster if you carry it with you than if you send it by radio. Imagine sending a data package to a colony 10 light-years away. By radio, it takes 10 years, but if you load it onto a warp ship and travel there yourself, you could deliver it in a week. This would fundamentally change how interstellar civilizations organize themselves. You'd probably see the emergence of courier ships, vessels whose sole purpose is to carry information between star systems. There's also a darker side to consider. Warp drive technology could be weaponized. Remember that blast of accumulated energy when a warp bubble collapses? That could be used deliberately as a weapon. You could create a warp bubble, aim it at a target, and then collapse it, releasing devastating amounts of energy. A warp drive could be the ultimate weapon, capable of destroying entire planets with a precision that makes nuclear weapons look crude by comparison. This raises profound ethical questions. Should we even try to develop warp drive technology? If it's possible that any sufficiently advanced civilization would discover warp drives, and if warp drives can be weaponized this way, does this help explain the Fermi paradox? That's the puzzle of why we haven't detected any alien civilizations despite the vast number of potentially habitable planets in the galaxy. Maybe civilizations that develop warp drives tend to destroy themselves either accidentally or through warfare. Let's shift gears and talk about the experimental evidence, or rather, the lack of it. Everything I've described so far is theoretical. No one has ever created even the tiniest warp bubble in a laboratory. No one has even proven that negative energy can exist in the quantities needed, let alone that it can be controlled and shaped into the precise geometry a warp drive requires. We're building castles of mathematics without knowing if the foundation is solid. But that doesn't mean experiments are impossible. There have been some intriguing proposals. Harold White, the physicist who's done so much work on refining warp drive theory, conducted experiments at NASA's Johnson Space Center several years ago. He used an instrument called a White-Jude warp field interferometer designed to detect tiny distortions in space-time that might be created by a microscopic warp field. The experiments used high-voltage capacitors arranged in a specific geometry to try to create a measurable effect. The results were ambiguous. Some measurements suggested tiny anomalies, but they were at the very edge of what the instruments could detect. They could easily have been experimental noise or systematic errors. The scientific community remains skeptical, and rightly so. Extraordinary claims require extraordinary evidence, and so far, the evidence for laboratory warp fields is far from extraordinary. But here's what's exciting. The theoretical work is advancing rapidly. Just in the past few years, we've seen multiple papers proposing new warp drive geometries, each one addressing different problems with previous designs. The irrotational warp drive reduces negative energy requirements. The segmented design improves stability and controllability. Other researchers are exploring warp drives that move at subluminal speeds, slower than light but still fantastically fast by human standards, which might be easier to create. There's a concept called a subluminal warp drive that's particularly interesting. Instead of trying to exceed light speed, you create a warp bubble that moves at, say, 90% of light speed. This is still slower than light, so many of the causality problems disappear. You don't create an event horizon. You don't accumulate as much matter and energy at the front of the bubble, and most importantly, the energy requirements drop dramatically. A subluminal warp drive might need only the energy output of a large nuclear reactor instead of the energy output of a star. Now 90% of light speed is still incredibly fast. At that speed, you could reach Proxima Centauri in about 4.7 years. That's much slower than a superluminal warp drive, but it's still far faster than anything we can currently achieve. The Parker Solar Probe, the fastest human-made object ever created, reaches speeds of about 0.04% of light speed at its fastest. A subluminal warp drive would be over 2,000 times faster than that. Here's something that might surprise you. We actually see something like warp drive effects in certain astrophysical situations. When a massive star explodes as a supernova, it creates a shock wave that expands outward through space. This shock wave can accelerate particles to incredible energies, creating what are called cosmic rays. The physics of how these shock waves accelerate particles involves some of the same mathematics as warp drive physics. Space is being compressed and expanded, creating gradients in space-time that accelerate particles. Similarly, in the jets of matter shooting out from black holes, we see matter being accelerated to speeds approaching light speed. The mechanism involves the twisting and warping of space-time around the rotating black hole. While this isn't quite the same as an Alcubierre warp drive, it shows that nature can and does create dramatic distortions in space-time that move matter in surprising ways. If nature can do it, perhaps we can learn to do it too. Let's dive deeper into the quantum mechanical aspects of warp drives, because this is where things get truly strange and where some of the biggest unknowns lie. Quantum mechanics, the physics of the very small, and general relativity, the physics of gravity and space-time, are two of the most successful theories in all of science, but they don't play nicely together. We don't have a unified theory of quantum gravity, and that's a huge problem when you're trying to understand something like a warp drive. Why does quantum mechanics matter for warp drives? Because the exotic matter or negative energy needed for a warp drive operates at quantum scales. The Casimir effect, our best candidate for producing negative energy, is a purely quantum phenomenon. It arises from the fact that empty space isn't actually empty. The quantum vacuum is a seething foam of virtual particles constantly popping into and out of existence. These virtual particles exist for incredibly brief moments, borrowing energy from the vacuum and then paying it back, all in accordance with Heisenberg's uncertainty principle. When you place two conducting plates very close together, you restrict which virtual particles can exist between them. Only particles with wavelengths smaller than the gap between the plates can appear in that space. Outside the plates, all wavelengths are allowed. This creates an imbalance in the quantum vacuum pressure. There are more virtual particles pushing on the outside of the plates than on the inside. The net result is that the plates are pushed together by what appears to be negative pressure, or equivalently, negative energy. This effect has been measured in laboratories. It's real, and it's tiny. The force between two plates 1 micrometer apart is about 1/10,000,000th of a Newton per square meter. To put that in perspective, atmospheric pressure is about 100,000 newtons per square meter. The Casimir force is incredibly weak. Scaling this up to create the negative energy needed for a warp drive would require structures of breathtaking precision over enormous areas. We're talking about maintaining gaps smaller than a wavelength of visible light across structures the size of a building or larger, all in the vacuum of space, all while generating and controlling the warp field. But there's another quantum effect that complicates things even further. When you have extreme curvatures of space-time, like those at the edge of a warp bubble, quantum field theory predicts something called particle creation. The vacuum itself can be excited by the intense gravitational fields, causing it to produce real particles rather than just virtual ones. This is similar to what happens near the event horizon of a black hole, the process that creates Hawking radiation. If a warp bubble creates Hawking-like radiation, that's a problem for several reasons. First, it costs energy. Creating these particles requires energy to come from somewhere, and that somewhere is probably the warp field itself. This could drain energy from the warp bubble, potentially causing it to collapse. Second, these particles would be produced all around the bubble, potentially interacting with the bubble in unpredictable ways. Third, the radiation itself could be dangerous to anything inside or near the bubble. Some physicists have calculated how much Hawking radiation a warp bubble might produce. The answer depends on the size of the bubble and the sharpness of the space-time curvature at its edges. Smaller bubbles with sharper edges produce more radiation. Larger bubbles with gentler transitions produce less. This suggests that if you want a stable warp bubble, you should make it as large as possible and ensure the transition from flat space-time inside to warped space-time outside is as smooth as possible. This brings us to the concept of warp bubble thickness. In most theoretical models, the warp bubble has 3 regions: flat space-time inside where the ship sits, highly warped space-time forming the bubble wall, and normal space-time outside. The bubble wall is where all the interesting physics happens. The thicker you make this wall, spreading the transition over a larger distance, the gentler the curvature and the less likely you are to trigger catastrophic quantum effects. But there's a trade-off. A thicker bubble wall requires more total energy to maintain because you're warping a larger volume of space-time. A thinner wall concentrates the warping, requiring less total energy but creating more extreme conditions that might trigger quantum instabilities. Finding the optimal balance is one of the many engineering challenges that would need to be solved. Now let's talk about the possibility of naturally occurring warp bubbles. This might sound bizarre, but some physicists have speculated that certain extreme astrophysical events might create temporary warp-like distortions in space-time. For example, when two black holes merge, they create ripples in space-time that we detect as gravitational waves. During the merger, in the immediate vicinity of the black holes, space-time is being stretched and compressed in violent, chaotic ways. Could these distortions ever arrange themselves into something resembling a warp bubble? Almost certainly not in any stable or useful way. But the question is interesting. If nature can create even temporary warp-like geometries, that tells us something about what's physically possible. Gravitational wave observatories like LIGO, Virgo, and the upcoming LISA space-based detector are giving us unprecedented views of extreme space-time dynamics. We're watching the universe perform experiments in general relativity that we could never replicate in a laboratory. There's also a fascinating connection between warp drives and wormholes. Both are solutions to Einstein's equations that involve exotic geometry and often require negative energy. A wormhole is like a tunnel through space-time connecting two distant locations. In theory, you could enter one end of a wormhole on Earth and emerge from the other end near Alpha Centauri, having traveled 4 light-years without actually crossing the space in between. It's a shortcut through higher dimensions. The mathematics of wormholes and warp drives share many similarities. Both involve manipulating space-time in ways that allow faster-than-light travel without technically breaking the light-speed barrier. Some researchers have explored hybrid concepts, like using a warp drive to traverse a wormhole, or creating mini-wormholes as part of the warp drive mechanism. These ideas are highly speculative, but they illustrate how different exotic geometries in general relativity are interconnected. Let's consider the sociology and philosophy of warp drive development. If humanity ever does develop this technology, it would represent one of the greatest achievements in our history. It would rank alongside the development of language, agriculture, and the scientific method as a turning point in what our species can do. But great power comes with great responsibility, as the saying goes. Who would control warp drive technology? Would it be governments, corporations, or some international body? The technology would be so powerful and potentially so dangerous that its development and use would need to be carefully managed. You couldn't just let anyone build a warp ship in their garage. The potential for accidents or misuse would be too great. We'd need international treaties, safety regulations, licensing requirements. The whole framework of space law would need to be rewritten. And what about contact with alien civilizations? If warp drives are possible, and if the engineering challenges can eventually be overcome by any sufficiently advanced civilization, then it's reasonable to assume that any aliens we encounter might also have warp drive technology. This changes the calculus of interstellar exploration and contact. Instead of civilizations being isolated by vast distances, unable to interact meaningfully, warp-capable civilizations could span the galaxy, establishing trade routes, diplomatic relations, or possibly even conflicts. This brings us back to the Fermi paradox in a different light. If warp drives are possible, and if they've been developed by alien civilizations, where are they? Why haven't they visited us? One possibility is that they have, but we haven't recognized the signs. Another is that warp-capable civilizations are rare because the technology is so difficult to develop. A third, darker possibility is that something about warp drive technology or its consequences tends to limit how long civilizations survive after developing it. Some scientists have proposed what's called the Great Filter hypothesis. This is the idea that there's some extremely difficult step or challenge in the development of intelligent civilizations that most don't survive past. Maybe it's the origin of life itself. Maybe it's the development of multicellular organisms or intelligence. Or maybe it's something in our future, like developing powerful technologies such as warp drives or artificial intelligence without destroying ourselves in the process. Let's explore the connection between warp drives and the structure of space-time itself at the deepest level. When Einstein developed general relativity, he showed us that space-time is not a fixed stage on which events unfold. It's a dynamic entity that can bend, ripple, and flow. But even Einstein might have been surprised by some of the exotic solutions to his equations that we've discovered since. The Einstein field equations relate the curvature of space-time to the distribution of matter and energy within it. They're a set of 10 coupled nonlinear partial differential equations, which is a fancy way of saying they're extraordinarily complex. Finding exact solutions to these equations is notoriously difficult. The Schwarzschild solution, describing the space-time around a non-rotating black hole, was discovered in 1916, just months after Einstein published his theory. But many other important solutions took decades to find. The Alcubierre metric, discovered in 1994, was a latecomer to the party. What makes it so remarkable is that Alcubierre worked backward. Instead of specifying a distribution of matter and energy and then solving for the resulting space-time curvature, he specified the space-time geometry he wanted, a bubble that moves faster than light, and then calculated what kind of matter and energy distribution would be needed to create it. The answer he got involved negative energy density, which is why the concept has remained theoretical. But here's something profound. The fact that you can write down a consistent solution to Einstein's equations that describes a warp drive tells us something important about the nature of space-time. It tells us that the universe's laws don't explicitly forbid this kind of geometry. Whether or not we can actually create the conditions needed is a different question, but the universe's fundamental structure at least permits the possibility. This is similar to how black holes were initially viewed. When Schwarzschild first found his solution, many physicists, including Einstein himself, doubted that such objects could actually exist in nature. The idea of a region of space-time so warped that nothing could escape seemed too extreme, too bizarre. But we now know that black holes not only exist but are common. There's a supermassive black hole at the center of nearly every large galaxy, including our own Milky Way. Could warp drives follow a similar trajectory? From mathematical curiosity to theoretical possibility to eventual reality? It's too early to say, but the pattern suggests we shouldn't dismiss ideas just because they seem exotic. Nature has repeatedly shown itself to be stranger than we imagined. Let's dig into the geometry of the warp bubble more carefully. Imagine you're an ant living on the surface of a balloon. Your entire universe is this two-dimensional surface. Now imagine someone starts inflating the balloon. From your perspective as an ant, the distance between any 2 points on the balloon is increasing. Space itself is expanding. This is analogous to cosmic expansion, and it's also analogous to what happens behind a warp bubble. Now imagine that instead of the whole balloon inflating uniformly, someone pinches it in one spot, creating a region where the surface is compressed, and simultaneously pushes out another spot, creating a region where the surface is expanded. If this deformation moves across the balloon surface, carrying a tiny ship sitting at the boundary between the compressed and expanded regions, you've essentially created a two-dimensional analog of a warp drive. The ship doesn't move across the balloon's surface. The surface itself deforms in such a way that the ship's position changes. This is the essence of warp drive: motion without movement, travel without traversing. The ship remains stationary relative to its local space-time while its position in global space-time changes dramatically. But space-time isn't a two-dimensional surface. It's a four-dimensional manifold. 3 dimensions of space and 1 of time, all interwoven in complex ways. The mathematics that describes this is differential geometry, the same mathematics Einstein used. It involves concepts like metric tensors, Christoffel symbols, Riemann curvature tensors, and geodesics. These aren't just abstract mathematical objects, they represent real physical properties of space-time, how distances are measured, how particles move, how gravity manifests. When you create a warp bubble, you're manipulating these geometric properties in a very specific way. The metric tensor, which describes how to measure distances in space-time, has a very particular form in the Alcubierre metric. It includes what's called a shift vector that depends on both space and time. This shift vector is what creates the compression in front and expansion behind. Calculating the energy density required to produce this geometry involves computing the Einstein tensor from the metric and then using the Einstein field equations to relate it to the stress-energy tensor. The stress-energy tensor is the object that describes the distribution of matter and energy in space-time. For normal matter, like the matter you and I are made of, this tensor has certain properties. It's positive, definite in certain ways. But for the Alcubierre metric, the stress-energy tensor has negative components. This is the mathematical signature of exotic matter that violates what physicists call energy conditions. There are several different energy conditions in general relativity, each describing reasonable assumptions about what kinds of matter and energy should exist. The weak energy condition says that energy density should be positive for any observer. The null energy condition is a slightly weaker version. The dominant energy condition says that energy shouldn't flow faster than light. The strong energy condition relates to whether gravity is attractive or repulsive. Normal matter satisfies all these conditions. But the Alcubierre warp drive violates at least the weak and null energy conditions. This is what makes it exotic. The recent breakthrough with irrotational warp drives is that they minimize these violations. They still violate the energy conditions, but only in small, specific regions, and the magnitude of the violation is much smaller than in previous designs. Some physicists have speculated about whether quantum field theory might provide a loophole. In quantum field theory, the energy density can be negative in certain situations, like the Casimir effect I mentioned earlier. But these negative energies are typically very small and very localized. They're also usually accompanied by positive energies nearby, so that the total integrated energy remains positive. Whether you can create the large-scale negative energy needed for a warp drive using quantum effects is one of the biggest open questions in the field. There's also the question of whether the universe might contain naturally occurring exotic matter that we just haven't discovered yet. Dark energy, the mysterious force driving cosmic acceleration, behaves in some ways like it has negative pressure. Could dark energy be harnessed for warp drives? Some researchers have explored this idea, but it's deeply speculative. We don't even know what dark energy is, let alone how to manipulate it. Another exotic possibility involves something called phantom energy, a hypothetical form of energy even stranger than dark energy. Phantom energy would have an equation of state where the pressure is more negative than the energy density. This leads to bizarre predictions like the Big Rip scenario, where the universe eventually tears itself apart. If phantom energy exists, it might be useful for warp drives, but that's a big if piled on top of many other ifs. Let's shift to the engineering perspective again. Suppose you had access to exotic matter with the right properties. How would you actually build a warp drive? The current thinking involves creating a carefully shaped distribution of this exotic matter around your ship. The geometry matters enormously. You need to create compression in front and expansion behind with a smooth transition between them and a bubble of flat space-time in the middle where your ship sits. One proposed design uses toroids, donut-shaped rings of exotic matter positioned around the ship. By varying the density and position of these toroids, you could tune the warp field geometry. The segmented warp drive concept takes this further, using multiple cylindrical structures arranged around the ship, each generating part of the overall field. This modular approach might be easier to construct and control than a single unified field. Control is a critical issue. Once you've created a warp bubble, how do you steer it? How do you speed up, slow down, or stop? Remember, from inside the bubble, you're not moving at all. You can't use conventional thrusters because you're not pushing against anything. Instead, you'd need to modify the warp field itself, changing the distribution of exotic matter to alter the bubble's properties. This suggests that a warp drive would need incredibly sophisticated control systems, probably computer-controlled, because the calculations would be too complex for humans to perform in real time. You'd need sensors to monitor the warp field, actuators to adjust the exotic matter distribution, and fail-safes to shut everything down safely if something goes wrong. The engineering complexity would be staggering, even if we somehow solve the fundamental physics problems. Now let's explore what happens at the boundary of a warp bubble, because this is where the physics becomes extraordinarily complex and where many of the practical challenges emerge. The edge of the warp bubble is not a sharp discontinuity. It's a transition region where space-time smoothly changes from the flat geometry inside the bubble to the highly warped geometry of the bubble wall, and then back to normal space-time outside. The thickness of this transition region is crucial. If the transition is too abrupt, the curvature becomes extreme, potentially triggering quantum instabilities and requiring enormous amounts of energy. If the transition is too gradual, the bubble becomes large and diffuse, also requiring vast amounts of energy to maintain. There's an optimal thickness that minimizes energy requirements while avoiding quantum catastrophes, and finding that optimum is a major focus of current research. The mathematics describing this transition involves what's called the shape function in the Alcubierre metric. This function determines how quickly space-time transitions from flat to warped as you move away from the center of the bubble. Alcubierre originally used a hyperbolic tangent function, which creates a smooth but relatively sharp transition. More recent work has explored other shape functions that might have better properties. Chris van den Broek, in his modifications to the Alcubierre drive, proposed a shape function that creates a much larger bubble on the outside, but compresses down to a tiny region on the inside. Imagine a soap bubble that's a kilometer across on the outside, but only a few meters across on the inside. This seems impossible in ordinary three-dimensional space, but in the curved space-time of general relativity, such geometries can exist. The advantage is that the larger external size means more gradual curvature and lower energy requirements, but this creates its own problems. If the interior is much smaller than the exterior, what happens to objects trying to cross the boundary? The transition would involve extreme spatial distortions. Matter trying to enter or exit the bubble would experience tidal forces, the same kind of forces that would tear you apart near a black hole. For a ship and crew to survive, these tidal forces would need to be manageable, which places constraints on how extreme the geometry can be. There's also the question of what happens when two warp bubbles interact. Suppose you have two ships, each in its own warp bubble, and they approach each other. The space-time around each ship is highly warped. When these warped regions overlap, you get a superposition of two complex geometries. The mathematics becomes fiendishly complicated. It's possible the bubbles would simply pass through each other without interacting, like waves crossing in a pond. It's also possible they would interfere destructively, causing both bubbles to collapse. Or they might merge into a single, larger bubble containing both ships. Nobody knows for sure because solving the Einstein field equations for two interacting warp bubbles is beyond our current mathematical capabilities. This is one of the many problems that would need to be solved computationally using numerical relativity, the same techniques used to model colliding black holes. But while black holes are natural objects that we can observe, warp bubbles are theoretical constructs, making it harder to know if our simulations are accurate. Let's talk about detection and observation. If someone created a warp bubble, how would we know? What would be the observable signatures? This is not just an academic question. If alien civilizations have developed warp drives, we might be able to detect evidence of their use, even if we never directly encounter the aliens themselves. One signature would be gravitational waves. A warp bubble moving through space creates disturbances in space-time that propagate outward as gravitational radiation. The frequency and amplitude of these gravitational waves would depend on the size and speed of the bubble. Current gravitational wave detectors like LIGO are tuned to detect waves from massive astrophysical events like merging black holes, but future detectors might be sensitive enough to detect artificial gravitational waves from warp drives if they exist. Another signature would be the energy released when a warp bubble collapses. As I mentioned earlier, the matter and radiation accumulated at the front of the bubble would be released in a powerful forward beam. This would create a distinctive signal, possibly detectable across interstellar distances. Some researchers have proposed looking for these signatures in astronomical data, searching for unexplained bursts of energy that might indicate warp drive activity. There's also the possibility of detecting the exotic matter itself. If warp drives require large quantities of exotic matter, and if this matter has observable properties, we might be able to detect it directly. This assumes exotic matter can exist in stable configurations outside of a warp bubble, which is uncertain, but if it can, it might have distinctive spectroscopic signatures, unusual gravitational effects, or other properties that would make it detectable. Now let's consider the thermodynamics of warp drives. One of the most fundamental laws in physics is the second law of thermodynamics, which says that entropy, roughly speaking, disorder, always increases in closed systems. This law is so fundamental that it defines the arrow of time, the distinction between past and future. Does a warp drive violate the second law? This is a subtle question. Inside the warp bubble, thermodynamics works normally. Time flows forward, entropy increases, everything behaves as expected. But the warp bubble itself is not a closed system. It's exchanging energy with the surrounding space-time through the exotic matter distribution that maintains it. The total system, bubble plus surrounding space-time, must still obey the second law, but the distribution of entropy between inside and outside the bubble can be complex. Some physicists have worried that the event horizon formed by a faster-than-light warp bubble might have thermodynamic properties similar to a black hole horizon. Black hole horizons have entropy, a fact discovered by Stephen Hawking and Jacob Bekenstein. If warp bubble horizons also have entropy, this could lead to complicated thermodynamic effects, possibly including the emission of Hawking-like radiation that I mentioned earlier. There's also a connection to something called the holographic principle, one of the deepest ideas in modern theoretical physics. The holographic principle suggests that all the information in a volume of space can be encoded on the boundary of that volume, like a hologram. This principle emerged from studies of black hole thermodynamics and has profound implications for quantum gravity. If the holographic principle is correct, it might place fundamental limits on warp drives. The amount of information that can be contained within a warp bubble might be limited by the surface area of the bubble boundary, not its volume. This could constrain how small you can make the bubble for a given amount of cargo or how much energy is required to maintain it. These are speculative connections, but they illustrate how warp drive research touches on the deepest questions in physics. Let's return to the practical side for a moment. Suppose we're a century or two in the future, and humanity has somehow developed a working warp drive. What would space travel look like? Interestingly, warp drives would probably not replace all other forms of propulsion. They'd be used for long-distance interstellar travel, but for shorter trips within a solar system, conventional rockets or ion drives might still be more practical and economical. Think of it like modern transportation. We don't use airplanes to travel across town. We use cars or buses or bicycles. Airplanes are for long-distance travel where their speed advantage outweighs their cost and complexity. Similarly, warp drives would probably be reserved for trips between star systems with conventional propulsion handling shorter journeys. This creates an interesting picture of future space infrastructure. You might have warp gates or warp stations positioned at the edges of solar systems, where ships activate their warp drives for interstellar jumps. Within the solar system, you'd travel conventionally. This would be safer, avoiding the risk of releasing accumulated energy near populated areas when the warp bubble collapses. The economics of warp travel would be fascinating. If warp drives require enormous amounts of energy or exotic matter, that creates natural limits on how many ships can operate and where they can go. Interstellar trade might focus on high-value goods, information, rare materials, perhaps even passengers willing to pay premium prices. Bulk cargo might still be too expensive to transport except in special circumstances, or perhaps the energy requirements could be reduced enough that warp travel becomes relatively routine. If we could harvest stellar energy efficiently, using structures like Dyson spheres or swarms, the energy cost of warp drives might be manageable. A civilization capable of building and operating warp drives would almost certainly be a Type 2 or Type 3 civilization on the Kardashev scale, capable of harnessing the energy output of stars or even entire galaxies. Let's explore some of the alternative warp drive concepts that have been proposed, because the Alcubierre drive, while the most famous, is not the only game in town. Physicists have proposed numerous variations, each trying to address different problems or optimize different aspects of the design. One interesting variant is the Natario drive, proposed by José Natario in 2001. While the Alcubierre drive creates expansion and contraction of space, the Natario drive works more like shearing or sliding space-time. Imagine space-time as layers that can slide past each other, like geological strata during an earthquake. The Natario drive creates a shearing motion that carries the ship forward. Mathematically, it has some advantages over the Alcubierre drive, particularly in how it handles acceleration and the distribution of exotic matter. Then there's the Krasnikov tube, proposed by Sergei Krasnikov in 1995. This isn't quite a warp drive in the traditional sense. Instead of creating a bubble around a ship, you create a tunnel or tube through space-time connecting your origin and destination. Once created, this tube allows faster-than-light travel through it. The clever thing is that you only need exotic matter to maintain the tube's entrance and exit, not throughout its entire length. The downside is that you have to travel to your destination conventionally the first time to lay down the tube. It's like building a highway before you can drive on it. The Krasnikov tube has an interesting property regarding causality and time travel. Unlike some warp drive designs, it's been proven that you can't use a single Krasnikov tube to travel backward in time. However, if you have two tubes with the right configuration, time travel might still be possible. This brings us back to the fundamental connection between faster-than-light travel and causality violation. It keeps showing up in different forms no matter which design you choose. Another approach is the quantum vacuum plasma thruster, sometimes called the Q drive. This concept, explored by physicists including Harold White, tries to exploit quantum vacuum fluctuations more directly. The idea is to manipulate the quantum vacuum in such a way that it creates a pressure differential, pushing the ship forward. While this isn't exactly a warp drive, you're not contracting space in front, it might provide a stepping stone toward warp drive technology by teaching us how to manipulate vacuum energy. There's also been work on what are called superluminal warp drives with reduced causality violations. These designs accept that you're going to have some issues with causality, but they try to minimize them. They do this by carefully engineering the warp bubble geometry so that the region where causality is violated is as small as possible, ideally smaller than the ship itself. If the causality-violating region doesn't extend beyond the ship, then at least the external universe maintains consistent causality, even if things get weird inside the ship. Some researchers have explored asymmetric warp drives where the bubble is not spherical or symmetric. An elongated, cigar-shaped bubble might have advantages for certain types of travel. A flat, disc-shaped bubble might be easier to generate and control. The optimal shape probably depends on your engineering constraints and what you're trying to optimize: energy efficiency, speed, stability, or controllability. There's even been speculation about biological warp drives. This sounds like pure science fiction, but bear with me. If certain exotic matter configurations are energetically favorable, and if evolution had billions of years to work with, could biological organisms evolve the ability to manipulate space-time? This would require the laws of physics to permit naturally occurring negative energy in biological systems, which seems extremely unlikely. But it's a reminder that we shouldn't assume technology always looks like what we humans would build. An alien warp drive might be as different from our concepts as a bird is from an airplane. Both fly, but through very different mechanisms. Let's talk about the computational challenges of designing and operating a warp drive. The mathematics involved is extraordinarily complex. Just calculating the space-time geometry for a simple static warp bubble requires solving complex differential equations. For a dynamic, moving, accelerating warp bubble, you need to solve time-dependent equations in four-dimensional curved space-time. This is computationally intensive, even with modern supercomputers. But it gets worse. If you want to optimize the design, minimize energy requirements, avoid causality violations, ensure stability, you're not just solving equations, you're searching through a vast parameter space of possible designs. This is an optimization problem in a high-dimensional space where each point requires solving difficult equations to evaluate. It's the kind of problem where artificial intelligence and machine learning might be essential tools. Some researchers have already started applying machine learning to warp drive design. Neural networks can be trained to predict the properties of different warp bubble geometries without having to solve the full equations every time. Genetic algorithms can search through design space, evolving better and better solutions over many iterations. These computational tools might be essential for turning warp drives from theoretical curiosities into practical designs. Now let's consider the infrastructure needed to support warp-capable civilization. If warp drives are real and practical, you'd need supporting technologies and infrastructure. You'd need exotic matter factories, facilities capable of producing and storing the exotic matter needed for warp bubbles. These would probably be massive structures, perhaps orbiting stations or asteroid-based facilities, far from populated areas for safety. You'd need navigation systems capable of plotting courses through interstellar space. Unlike travel within a solar system, where you can use planets and the Sun as reference points, interstellar navigation requires tracking your position relative to the galaxy as a whole. You'd probably use pulsars, rapidly rotating neutron stars that emit precise radio pulses, as cosmic lighthouses. Pulsar navigation is something NASA and other space agencies are already developing for future deep space missions. You'd need communication networks. Even with warp drives, maintaining contact across interstellar distances would be challenging. You might establish relay stations at key points with courier ships carrying data between systems, or perhaps you'd develop quantum communication techniques that could send information faster than light, though this runs into the same causality problems as warp drives themselves. You'd need rescue and recovery services. What happens when a warp drive fails while a ship is between stars? Can you send a rescue mission? How do you even locate a disabled ship in the vastness of interstellar space? These are practical problems that a warp-capable civilization would need to solve. Perhaps warp ships would travel in convoys, so help is always nearby. Or perhaps each ship would carry redundant systems, multiple warp drives, so that if one fails, others can compensate. There's also the question of space traffic control. If multiple warp ships are operating in the same region, how do you prevent collisions? Do warp bubbles even collide in the conventional sense, or do they pass through each other? If they can collide, what happens? Presumably, you'd need to establish space lanes, designated routes through space where warp travel is permitted, with regulations about speeds, bubble sizes, and safety margins. Let's think about the first warp drive test. If humanity ever builds a prototype warp drive, how would we test it safely? You couldn't just activate it near Earth. If something went wrong, if the bubble collapsed catastrophically, releasing accumulated energy, you could damage or destroy everything nearby. The first test would need to happen far from any inhabited areas, probably beyond the orbit of Neptune or even in the Kuiper Belt. But testing far from Earth creates its own problems. How do you monitor and control the test? Radio signals from Earth take hours to reach the outer solar system. If something goes wrong during the test, ground control would find out hours later, far too late to intervene. The test vehicle would need substantial autonomy, probably with an AI system capable of making decisions in real time. The test protocol might involve creating the smallest possible warp bubble, moving it the shortest possible distance at the slowest possible speed, perhaps just barely exceeding the speed of light. You'd measure everything: energy consumption, space-time curvature, gravitational wave emission, particle production, every observable quantity. Only after extensive testing at minimal parameters would you gradually increase the scale. Let's bring this all together and think about what warp drives mean for humanity's future and our place in the cosmos. If warp drives are possible, even in principle, it fundamentally changes our relationship with the universe. We're no longer trapped in our solar system, limited to painfully slow journeys to neighboring stars. The galaxy becomes accessible. Thousands, perhaps millions of worlds become reachable within human lifetimes. This would trigger a transformation comparable to any in human history. When our ancestors left Africa and spread across Earth, they encountered new environments, new challenges, and new opportunities that shaped human evolution and culture. When Europeans crossed the Atlantic, it began a process of globalization that continues today. Warp drives would begin a process of galactic integration, connecting civilizations across light years. But let's be realistic about the timeline. Even in the most optimistic scenarios, warp drives are not something we'll see in the next few decades. The breakthroughs needed, understanding quantum gravity, discovering or creating exotic matter, developing the engineering capabilities, represent challenges that will likely take centuries to solve, if they can be solved at all. The path forward probably involves several stages. First, we need better theories. We need a working theory of quantum gravity that unifies general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches are being actively researched, but we don't yet know which, if any, is correct. This theory might reveal whether exotic matter can exist in the quantities needed, or it might show that warp drives are fundamentally impossible. Second, we need better experiments. We need to measure the Casimir effect more precisely, study quantum vacuum fluctuations in more detail, and look for any signs of naturally occurring negative energy. We need to improve our gravitational wave detectors to the point where we could detect artificial gravitational waves if they exist. We need to push our understanding of space-time to its limits. Third, we need better engineering. Even if the physics works out, building a warp drive would be a supreme engineering challenge. We'd need to develop technologies for manipulating matter and energy at scales we currently can't imagine. This might require advances in nanotechnology, quantum computing, fusion power, and countless other fields. The societal implications would be profound. Space law would need complete revision. Questions of jurisdiction, property rights, environmental protection, and safety regulation would all need to be answered for a galaxy-spanning civilization. Who owns a planet? Can you claim an entire solar system? What are your obligations to any existing life forms you discover? The economic implications are equally vast. Interstellar trade could develop, though what would be traded is unclear. Information, certainly, scientific discoveries, cultural works, innovations, perhaps rare elements or materials that are abundant in some systems and scarce in others, maybe even passengers, people seeking new worlds to settle or explore. The cultural impact would be extraordinary. Meeting other civilizations, assuming they exist, would challenge our assumptions about life, intelligence, consciousness, and our place in the universe. Even without alien contact, the simple act of spreading to other star systems would create isolated populations that would gradually diverge, developing new cultures, perhaps even new subspecies over enough time. There are risks, of course. Any technology powerful enough to enable interstellar travel is powerful enough to be weaponized. A warp drive malfunction could release catastrophic amounts of energy. The ability to travel faster than light might enable time travel, with all its associated paradoxes and dangers. We'd need wisdom to match our technology, something humans have historically struggled with. But there are also immense opportunities. Warp drives could be our ticket to long-term survival as a species. Earth won't remain habitable forever. In about 1 billion years, the sun will grow hot enough to boil Earth's oceans. In 5 billion years, it will expand into a red giant, engulfing the inner planets. If humanity is still confined to Earth, these events mean our extinction. But if we've spread to other stars, we become resilient to any single catastrophe. Warp drives could also help us answer the deepest questions about the universe. Why does it exist? How did it begin? Are we alone? What is the ultimate fate of everything? By exploring the galaxy, studying other worlds, and perhaps meeting other minds, we gain new perspectives on these eternal questions. We learn not just about the universe, but about ourselves. The journey from where we are now to functioning warp drives, if it's possible at all, will be long and difficult. It will require the best efforts of countless scientists, engineers, and visionaries. It will require international cooperation on an unprecedented scale. It will require dedication, resources, and time measured in human lifetimes or even generations. But this is what humanity does. We dream of the impossible and then we make it real. We dreamed of flight, and now planes cross the globe in hours. We dreamed of going to the moon and we walked on its surface. We dreamed of talking to people on the other side of the world, and now we carry devices in our pockets that connect us to billions of people instantly. What seems impossible today becomes routine tomorrow, so while warp drives remain theoretical, while the challenges are immense, while the timeline is uncertain, the very fact that we can conceive of them, that we can write down the mathematics describing them, that we can identify the obstacles and begin thinking about solutions. All of this suggests that maybe, just maybe, the stars are not forever beyond our reach. The universe is vast, but it may not be unconquerable. Space is cold and dark and dangerous, but it may not be impassable. The speed of light is a formidable barrier, but it may not be absolute. And humanity, for all our flaws, has proven ourselves to be remarkably good at solving problems that seem impossible until we solve them. The warp drive journey is just beginning. Where it leads, only time will tell. If you made this far, please make sure to give this video a like. Your support means a lot. And if you found the physics of extreme conditions fascinating, you'll definitely want to check out the video at the left side of the screen. The terrifying truth about how cold space really is, because understanding the brutal reality of the space environment is crucial for anyone dreaming about interstellar travel. The extreme temperatures, radiation, and vacuum conditions of space present challenges that any warp-capable ship would still need to overcome. See you there.